I suppose, you know, I'm primarily about batteries, but you do need a motor to drive the car. That's what it's about. It started off at EVTV with AC motors, and they pretty much to this day, if you want to put pound and torque for the minimum dollar amount, that was still the choice. Unfortunately, actually fortunately, the batteries have gotten so much better, we've outrun the motor, and we've had a number of cases, not so much this year as we've hardly sold any, but the previous year, of people burning up motors simply because they could put them on the road for an hour and a half on the freeway, and the series AC motor is very difficult. Particularly with Mr. Brunka's brushes and commutator there, it's kind of a problem. So the last year or two, we've kind of driven toward AC motors, and high performance electric vehicle systems has kind of led that charge. Brian Seymour, his father, actually was in the motor business for many years. He started out rewinding washing machine motors for neighbors and friends and built a motor business. So that's a central part of our electric cars. It's generationally part of the Seymour family's genetic makeup. And so it's kind of interesting the trail they've been on, and specifically while we've been around. My brother lives in Texas. If you look out in the hall, we've got a yellow battery that's a 72 amp hour, 48 volt battery that fits right into the seat of a club car precedent. In Texas, golf cars are $20,000. They go 50 miles an hour, and they use them on ranches and for hunting and a lot of places where there is no golf at all. And Texas is like a big golf cart. In the early days of this century, Brian and his brother got into making big golf carts. And in fact, the name of the company used to be High Performance Golf Cars, I think. And they kind of invented or innovated some of the first AC motor applications in golf cars. Golf cars just didn't use AC motors. And they innovated that and kind of created their own little space doing it. And it drew some other attention. So a lot of their business increasingly had little to do with golf cars. Not entirely so much about us, but Zamboni machines, mining equipment, hydraulic pumps, and so forth, all like some of the advantages of an AC motor. Today, I understand bread trucks are very popular. All right, they for EVCON. But they kept the natural progression to a larger and larger motor. We discovered their kind of then top-of-the-line AC50. The best vehicle conversion EVTV ever did was my beloved English white speedster that some Eaton guys from Tokyo came and took away from me by force, offering me, I think, $57,000 for the car. I foolishly gave it to them. And I'm actually going to rebuild that car again at some point. But it was not a race car, but kind of elegantly everything balanced and tuned perfectly to me. And it was the best deal I've ever had in an electric car. I was stunned and delighted about, it's been nearly 2 years, when they had a sudden and violently explosive line extension, which for most companies that size should prove fatal, but instead they're thriving with it. And suddenly we had the new AC51, AC75, AC76, all based on the Curtis controller, which they do not manufacture, but has been around and is kind of a bulletproof controller. And I've just been fascinated when they limited to about 75 kilowatts. and facing some demand for larger, more powerful things. He basically put two rotors and two stators together on one shaft where you can use two controllers on one motor, and recently had the AC35 X2. We do Siemens motors and EVCON motors, but still probably the largest seller and kind of our flagship is the HPEVS motor line. And by doing that, he has a 150 kilowatt solution, maybe a little better if you push it. And so that's suddenly when we go from a suitable solution. I always thought cars 2,500 pounds or less, that pretty much extended them up through, I would say you could have a nicely driving 4,500 pound car, certainly with the 35 X2. And that covers 99% of the conversions you see, and all of it under the magic $10,000 mark. So it's an important part of our product line, and I think it's been a very enabling line extension for the EV community. And last year was Brian's first at EVCON, and he encountered Anna Wuppenberg, our boat guy, and as it turns out, in California, Brian's kind of a boat enthusiast. So there's been a turn of events, and I'm very pleased that that's kind of coming to light at this year's EVCON. Would you all please give a warm welcome to Brian Seymour and high performance marketing.
There we go. Can you hear me?
Nope.
No. There we go. Is that on now?
Yep.
Thank you, Jack. My name is Brian, and I'm a former BMS user. One day at a time. I thought you might like that. But I haven't drank all of the Kool-Aid yet. There's still a little bit left. So we're going to discuss some things that we've been working on and just playing around. Like Jack last year, over the last year, I got my papal decree and decided that I could make shit up all I want. So after last year's conference, we had this whole business plan for the next year. And after seeing Ane's video of his boat, I leaned over to Jack and I said, I got to ask permission from my wife to build a boat. And she's nodding her head. So we kind of just put together a plan, and we've been getting some calls over the last couple of years with people wanting to do boat conversions, and we decided we needed to come up with a new motor. So we started designing an oil-cooled stainless steel motor. So this is kind of the things that I'm going to discuss today. There's our boat. We're not going to be getting into the ski boat conversion business, but I like to go big. So we decided to do a ski boat just to prove that it can be done first off. I think Ane's already done that. But I like to go fast. So I wanted to see how fast I could make a ski boat go. So we picked this up for $7,000 out of an ad in the paper. And originally had a 4.3 liter, 205 horsepower V6 with a Alpha 1 outdrive on it. And big ugly thing, so we decided to put that in. The internals to this motor are virtually the same as the AC35 X2 we currently produce. The difference is, the frame is stainless steel, the shaft is stainless steel. The end bells here are eventually going to be anodized aluminum, and we put shaft seals, O-rings, seals around all the box, sealed connectors for the cables, sealed connector for the encoder, and it's not something that you can just drop into a bucket of water and run it, but it's pretty close. We do a small pressure test on it. We can pump up, 4 or 5 psi in there and hold that pressure. There we are, mounted in the boat. Since we are going to be getting, selling these to people that are going to want to convert, not necessarily a ski boat, but more of a harbor cruiser, a runabout, maybe a tender boat. We're making adapter plates and all the mounting and the flange shaft coupler, all to go with the Merc Cruiser parts. So when we're all done with this, somebody will be able to buy this kit and bolt it into a boat that has a Merc Cruiser setup. There's the motor with the chill plate installed on top. We modified the original chill plate that we currently produce, and we made it fit right over the top of the adapter plates. So it makes a nice little package, and we probably are going to pre-assemble all of this before it ships. In this project, we're using the 1239-8501 Curtis controller, 144 volts, 500 amps. And here's the whole setup bolted together in the boat. In this project also, we chose to go with the CAM 72 cells. I got the last 144 that Keegan had of his original shipment. And we chose these mainly because the lightweight, smaller physical size, and really good energy density. And the information looked real good. So we went ahead and go with it, and it was kind of a risk. They're not cheap; they're quite a bit more expensive than the CA cells. But we felt, it was a good time to test them out. And we've got some performance data that we took on these batteries that everybody might be interested in. There's our whole setup completed in the boat. 144 of the CAM 72 cells, giving us nominal voltage of 153 volts at 210 amp hours. So we did a 3 parallel 48 series pack. These boxes here contain DC-DC converter and a couple other things we're going to talk about in the next couple of minutes. Let's back up here for a second. One piece of advice, I had a little discussion with Jack about this a couple days ago. These batteries come with some plastic brackets. I strongly recommend you use them. The batteries are coated in a real thin mylar heat shrink material. And the casing of the battery is actually aluminum. And if you put a voltmeter between the terminals and the case, you do get voltage. And what we found is if you pierce that mylar coating, you will get current flow to the battery pack. It's minor, it's very small, but it is enough to trip the GFI in the motor controller. So we had a couple of our battery racks, these are all made out of aluminum, and we had a couple of our battery trays just scrape it just a little bit and pierce through. And we had multiple spots in the pack that were essentially shorted to the pack, and we tripped the GFI in the motor controllers. So for the extra 100 thousandths that it adds to the battery, it's probably going to save you a lot of headache in the long run. We actually had to go in here and pull all the batteries out. That little white line there is a piece of Nomex. And we had to go around all the inside of the battery trays and around the top and insulate with Nomex to keep it from shorting out. And it's not a lot of current, but like I said, it is enough to trip the GFI in the motor controller and you'll get a fall. In lieu of a battery management system, this is something that we've been working on. This device right here is called a QD. It's a Curtis device. And it was primarily designed for lead acid batteries, material handling. And what they do is they take this unit and they mount it to a battery pack that goes in a forklift, and it stays with that battery pack. So it monitors charge going into batteries, charge coming out of batteries, it calculates state of charge based on amp hour counting, and it also runs a current versus voltage algorithm at the same time. So it kind of compares the two and comes up with the state of charge. That algorithm is completely useless for lithium batteries. So what we're doing is we're using it strictly as a monitoring device. We can use the amp hour counting, and then I wrote software for the motor controller to go ahead and calculate the state of charge, and then we can display it. We can do cutbacks, all kinds of things with it. And this is a bank charger. We're going to get into that in a minute. This is a schematic diagram of what we did in the boat. These are actually 3 cells, so they're 3 parallel on each of these. So we've got the acuity device with a current sensor, and then it's tied into the ends of 12 cells, or a bank of 12 cells. This acuity device draws a little bit of current, and I think it was John mentioned yesterday, one of the things you got to be real careful of is draining some power out of part of your pack and not matching that on the rest of it. So what we did to combat that is we added a low current charger, basically a laptop charger. Got this off of eBay for this right here for like $23. It has a maximum charge voltage of 42.5 amps, or 42.5 volts at 3 amps. So what we're doing is we're using this to keep the banks of cells balanced. So here's the whole system. We've got 4 acuities and 4 of these small chargers. And so that keeps each individual bank even with one another. But then we also have the 2.5 kW EVCON that charges the entire pack. Now we also, since the acuities are a CAN bus device, we're communicating to the motor controller via the CAN. The EVCON is a CAN bus device. So we're actually using the motor controller to do the charger controlling. So we bring in the voltage of each bank. We can then control the charger based on that voltage. So if we have one bank of cells that gets out of hand, we can shut down the EVCON charger and let the small laptop chargers finish off the charge on the rest of the pack. We shut off the EVCON charger at about 41.5 when the highest bank reaches 41.5 volts, which is right around 3.45 volts per cell. Then we go ahead and let the little laptop chargers finish off each bank to 42.5 volts, which is 3.54 volts per cell. Typically, the current is 2.8 to 3 amps. They do run during the bulk state of charge, so they are actually increasing your charge rate. Here we have a charge curve showing the bulk charge right here. So we're charging right at about 18 amps. And then up here we have the highest bank voltage and the lowest bank voltage. So we do actually monitor and we can display all of the bank voltages, but we really only care about the highest and lowest because we know the other 2 are in between. So probably right around in here, right where you see the current on the EVCON drop down to near 0, this green line right here is our highest bank. So it, no doubt, right about that point in time, got to about 41.5 volts. And we taper the current on the EVCON to maintain that 41.5. As soon as it goes above that, we shut off the EVCON, which happened right here. Well, not completely shut off. It was probably about, what was that, maybe 2-3 amps charge. And then we let the little laptop chargers take over. And you can kind of see what happens with the high and the low bank. This is our voltage delta right here. So at the top of the curve right here, where the EVCON did turn off completely, our bank delta was at about 1.6 volts between the highest bank and the lowest bank. Where at the bulk state of charge, we were down here, and I remember the test, it was 0.02 volts, so 200 millivolts between the highest and the lowest bank. That's one thing I noticed, you know, and we've never really done that kind of comparison before. You know, we've looked at high cell, low cell, but in banks of 12 cells like this, even under heavy loads, that voltage delta is really, really small. 2 to 20 millivolts, maybe 30 millivolts, even at 1,000 amps. So in this case here, probably what caused this is, obviously, you know, we had this green line here, our highest bank, a little bit higher voltage, is either the acuity drew off a little bit more power on the lower banks, or more likely than not, the chargers aren't all exactly 3 amps. Some of them are 2.8, some of them are 3. So what it is we had a bank that was lagging behind. And that's what this is designed to do, is it takes care of that lag. And it finishes off, you can see here, after, well, that happened about 4,000 seconds, so 6,000 seconds, or maybe 40 minutes later, our bank delta is all the way back down to 0.2 of a volt when it finished off. So, and that's what we're seeing on this is during charge and during a drive cycle, the differential between the banks is really low. And that's important because if that delta voltage gets too high, we can detect a problem in a bank. So whether we're charging or discharging, we're going along, we're on 300 amps, and we can monitor our high and low banks right here. And if we get a battery that goes sideways, a cell that goes sideways in one bank, then that delta is going to go way up. And we can detect that, we can throw a fault, we can display it, and alert you as to what's going on. This right here was in our boat. We did a idle to full speed test, and this would actually overlay a graphic we're going to show later. Started out at idle 5.7 amps, that's doing probably 3 miles an hour. Nailed the throttle to wood, and our maximum current throttle is 1,023 amps. This is the really cool part about these batteries, and Jack probably already knows this, but we only sag to 143.55 on a 153 nominal pack. At 1,000 amps, even in a 3 parallel system, that's really good. I know the SE cells, but that would probably be down in the 120s. So these cells can really kick up the power. So I was really impressed with that. And you know, we don't get a lot into batteries. You know, we're mainly motor guys. But occasionally we will build a project and we do some testing. And it's not real scientific. You know, it's usually just a couple runs around the block. But you know, we do try to gather some information so we can pass it on. Plus, it's good information for us. On the motor. Oil-cooled motors. Basically, what we're focusing on right now is the 8-inch motors, the AC34 and 35, which are virtually identical mechanically, except that the windings are a little different. The 50 to 51, the 50 primarily is used on, the 51 or 50 is primarily used on a 96 volt system, where the 50 is used on a 144 volt system. The 34X2, here again, that's for a lower voltage system, where the 35X2 is a higher voltage version of it. Right now, we have parts to build about 3 or 4 of each of these. So we're putting them into select hands for people that can give us some feedback in their application. So in the future, we're going to be doing the AC74, 75, 76. And right now, those particular motors are air over only. There's no cooling. So if you look at the torque speed curves on like an AC75 compared to an AC50, The AC75 continuous horsepower is only about 17 horsepower, where the AC50 is up around 40 horsepower. So I know a lot of guys are buying these motors thinking that since it's a bigger number, it's a bigger badass motor. And it kind of is when it comes to torque, but continuous running horsepower is kind of lacking on that motor. It was primarily designed to move a 15,000 pound mining vehicle at 10 miles an hour on 20% grade. So it works well on our car. We've got an AC75 in our Scion, and it'll run all day long. Yeah, not a problem. Yes, sir.
What's the impact on oil cooling for things like the pump and the hoses and the radiator that are expecting to have water or glycol or something?
Okay, yeah, we're getting to that. Okay. So the AC 74, 75, 76, everything's on the drawing board right now. We're getting ready to make parts. So we're expecting late fourth quarter. The new configuration it's only going to be available this way. We're going to obsolete the air over motor, and there will be then two options. You can do either oil cooling or just an air over application. And it'll just be a matter of removing the shaft seal and not fill it with oil. So the configuration of the motor will be the same. Why oil cooling? Okay, so the oil we use is a dielectric oil that you would find in big transformers. It's a great heat transfer. It's actually a purified mineral oil. It's very lightweight. It pours almost like water. So we use this because it gives us better heat transfer. The oil is in direct contact with all of the components inside the motor. We just run it right through. So it can gather up the heat from the windings, the stator core, and the rotor. And with just an air-over motor or a water-cooled motor where you've got a water-cooled jacket, you don't remove any heat from the rotor. It's just whatever transfers out. So that's why we opted for the oil cooling, is because we can just get a lot better heat transfer when we do it directly. Also bearing lubrication at some of the RPMs that we run. Sometimes we'll have issues with bearings because the grease just doesn't lubricate the bearing well enough, or it gets hot, because in that application we're running 5,000, 6,000, up to 8,500 RPM. It also lubricates the shaft seal. One other interesting thing we found with the oil cooling on the dyno is the air-cooled motors with the air flowing through the motor. Generally, when we get up to about 100 to 110 degrees C, they go into thermal runaway. There's nothing you can do to cool the motor down once it gets past that point, except just shut it down and let it rest. We found with the oil cooling, we could really control the temperature at the higher end. So when we did our dyno testing, we ran it at 130 degrees C, which is 266 degrees Fahrenheit, for several hours, and we could control that temperature perfectly. We didn't have thermal runaway issues. So I think the next slide, okay, yeah, here we go. Here's a basic schematic diagram, and this goes back to your question. In the boat, we're using a heat exchanger that is a Mercruiser product, and it's generally used for cooling the oil for the internal combustion engine. It gets water passed through it. And then for the controller, we're using a similar heat exchanger that is usually is for power steering in a boat. We have a small 12-volt pump for the coolant. Same thing we use in the automotive applications, a small reservoir, and then our chill plate. For the oil, we went ahead and chose to run an oil filter in this. We're not sure if you really have to do that because everything's pretty clean. We did it because on a prototype motor, the thing had been together and apart, metal shavings and all kinds of that stuff in it. So we wanted a filter to get all that stuff out of there. The oil pump we're using is readily available from Summit Racing. It's for the racing guys out there. It's used primarily for a manual transmission or the differential in a race car to cool the oil in those. rated continuous duty for 3 gallons per minute, up to 50 PSI. We don't get anywhere near that on the PSI though. Now, in an automotive application, what you would do is instead of using 2 different heat exchangers, you'd use a radiator out of a vehicle that had an automatic transmission and has the automatic transmission cooler built into the radiator. So that would be your hook motor heat exchanger. You connect the lines there where you originally connected to the transmission. And then the water from the radiator would be what you use to do the controller. And we haven't tested it, we haven't tried it yet, but theoretically, it should work. Not much of a different system than what we've already got, and with the amount of airflow over a radiator, you definitely wouldn't have any temperature problems. This is the cooling system in the boat. This hose right here brings in the water from the outdrive on an Alpha 1 outdrive. The seawater pump is built into the outdrive, so that makes it nice. We don't have to have an external water pump to pump the bulk of the water through. Run for a small heat exchanger here, like I said, for a power steering unit, for our little water pump. And then we come over to the heat exchanger here. That's originally for, I believe it was for a big block Chevy in a Merc Cruiser application. One thing that worked out really well on this is all of these hoses are all standard Merc Cruiser hoses. And so I managed to find them on eBay and various places, and made for a really nice clean setup. Here's the oil pump, made by Tilton. Like I said, $200, I believe is what they cost on Summit Racing, and does real well. No issue with heat or anything like that, since the heat that it's designed, the temperature it's designed for is a lot higher than what we're running. Okay, here's our video. Sorry, no champagne or colorful commentary like Ani did, but lots of EV grins. So I use a Verb camera, which has got GPS, and if I had the internet, this would actually be a map here, but it also includes speed and direction and altitude. So here we're starting to gather some data, different speeds, that sort of thing. We go ahead and run it up to 30 miles an hour.
Motor RPM on there?
It is in the graphs that we're going to be getting to.
What camera did you say?
It's a Garmin Verb. Yeah, and I actually use it for my flying. I mounted it in the plane, and that noise is not my boat. That's this guy over here doing like 80. Yeah, it's a really nice camera because it actually uses, it logs all your GPS locations, and you can actually display a Google Maps over here on the side, and it'll actually give your location. So it's really cool when I'm flying because I can tell exactly where I've gone, where I've been, how fast I was going, and my altitude and direction. Yeah, 30 miles an hour on the water seems really fast. Okay, so let's get to some performance charts. When taking on a boat project, I always had in the back of my mind, I've owned boats. Oh, I've been around boats since I was probably 5 years old, and I've owned personally 7 boats in the last 21 years. All different varieties of sizes and outdrives, jet drives, outdrives, whatever. And it's, I've always known in the back of my mind that it takes a lot of power to push a boat through water. But I didn't really realize how much until we built a budget boat. So, with Jack's calculations that he gave yesterday, the boat weighs 2,100 pounds. So a 2,100 pound car would take approximately 210 watt hours per mile. And that's a really close number. That's a really accurate number. And that's to travel at 60 miles an hour. At 30 miles an hour, like what we were doing in the boat, you would, in a car, you would be doing 150 to maybe 180 watt hours per mile. This was 10 times that.
Wow.
Here we are at 10 miles an hour. And the way we got our speed and everything is boats are set up with a pitot system, and they basically work on water pressure. So I got this crazy idea to just put a pressure transducer in that line and convert that signal into speed in the motor controller, and it worked. It actually worked really well. We calibrated it via GPS, and so all of our graphs, but we did have to clean the data up a little bit because the boat was bouncing, but the speed did actually come from the pressure transducer. So here we are at 10 miles an hour, and here's our motor RPM. We're roughly, I don't know, it's about maybe 1,850 RPM or so. And the top line is our battery current. So we're running roughly 130 to 135 amps at 150 volts to travel at 10 miles an hour. Our watt hours per mile are about 2,200 watt hours per mile. 15 miles an hour, it gets worse. 360 amps at 150 volts to go 15 miles an hour. Right at about 3,600, I think the actual number was 3,575 watt hours per mile to push a boat at 15 miles an hour. Now, the nice thing about a boat is eventually it's going to get on a plane, and that happens on this boat at about 17 to 18 miles an hour. So this is kind of interesting. We go to 20 miles an hour, and now our current, here we are 360 amps. Now we're down to about 330 amps, and our watt hours per mile dropped to 2,500 because we got up on a plane. So on a boat, you want to hit that sweet spot. There's a sweet spot. Just after plane, where you got the least amount of power for your speed. But then it gets worse. 25 miles an hour, 425 amps, just a little above 2,500 watt hours per mile. Motor RPM coming up, we're almost 3,500 RPM. 30 miles an hour. Still roughly around 2,500 watt hours per mile, but now we're up to 510 amps. That, folks, is 100 horsepower to push a 2,000-pound boat through the water at 30 miles an hour. In a 2,100-pound car, that would be about 10 horsepower to go 60 miles an hour. So they are an enormous power hog. 3,500 to 35 miles an hour, 630 amps, 2,650 on the watt hours per mile. So it doesn't go up exponentially like I expected it to. I expected our watt hours per mile to get a lot worse, but once you're up on the plane, the losses are fairly even. But you're already starting out in the hole really bad with the current. So here we are at 630 amps. With a 210 amp hour battery pack, you're not going to go very long. Here's an idle to full throttle test. We actually achieved 42 miles an hour in the boat. It planes out remarkably fast. The original internal combustion engine on this boat, we planed in about 5.5 to 6 seconds. If we look at 15 miles an hour, so we're right around in here. We planed out just a little over 4 seconds. So we did change the prop. We went from a 19 pitch prop to a 15 pitch prop. And we're going to do a little bit more work with that because at 5,000 RPM, which is the sweet spot on the motor, we're running 42 miles an hour. Well, at current draws like this, we don't need to run 42 miles an hour. And actually, this, if you take that earlier current max current of 1,000 amps. It lays right over the top of this. It's from the same data pole. So at 42 miles an hour, we were pulling a little over 1,000 amps. Sucking the juice. We're really after, you know, if we do something like a ski boat or a pleasure craft, really, you know, 25 to 30 miles an hour is plenty. And as we can see with the current draw and everything, it just is not practical to try to push them any faster. So we're going to re-gear the outdrive to where we'll have 5,000 RPM. Well, we get 5,000 RPM at about 27 to 28 miles an hour. And what that does for us is that'll relieve torque load on the motor and reduce motor heat. When we're cruising at 30 miles an hour, the motor runs about 120 degrees C. So we've hit basically its maximum limit, and that's 100 horsepower. So out of the AC 35 oil pool, we can run pretty close to 100 horsepower continuous out of it at 5,000 RPM. Other uses. The big one for us is going to be sailboats. There's a lot of sailboats that run diesel engines. They're usually 40 to 80 horsepower. We can replace them with electric drive and do it on battery power. There's even certain ports around the country that are really limiting now the diesel engines that are running in the port because of pollution. We're getting calls from Seattle. They've got some regulations going in there that they've got to start either putting emissions equipment on their diesels or get rid of them. And for sailboats, the nice thing about an AC drive is we've got all this unlimited regen power we can create. So they can use battery power and the electric motor to get in and out of the harbor. And then while they're under sail, we've got the prop is still turning, and we're generating electricity, and we're recharging the batteries. We use it in automotive, either radiator, like what we were discussing, mining, and a whole bunch of stuff that you guys haven't told me about yet, because I'm sure that you guys have come up with some wacko thing that you want to do. And that's basically it. Questions?
Energy you're using by running the oil through the motors?
You know, we ran some tests on it. It's minimal. We smooth the rotor. Normally we have fins on the rotor. We smooth all of that out. So it slings the oil around in there still, but it's not really creating a lot of drag. It's a very, very lightweight oil. It pours like water. So is there drag? Yeah, there's some drag. But we're probably, you know, getting any energy loss back in lower running temperatures.
Have you thought about using the motor at all as the pump? I mean, it's kind of already spinning, but would that move the oil enough to get it to flow? It's varying speed, so it's very spooling.
You'd have to have enough pressure to get it through the heat exchanger, possibly some rise up into a heat exchanger. The pump that we're using, the oil pump, draws about 3 amps at 12 volts. So it's really a minor on energy. Could we use the motor itself? Yeah, possibly, but that would probably make it a lot more complicated to build.
I was wondering, did you compare your displacement weight before and after your conversion?
Yes. Yes. Right now, the boat does not have the rear seat or the rear hatch on it. Our nearest estimates, you know, we weighed the boat before, and we did weigh it after, but we haven't added those components back on to reweigh it. As near as we can figure, we're going to gain 100 pounds.
It's also, can't be a mind talk, but is this cooling system going to allow us to get the curing temperature down on a permanent magnet motor, and therefore our performance yield way up in performance applications?
You'll have to ask the permanent magnet motor guy.
little device you use for Activision or a Coulomb counter, are you going to have some system for the automotive applications where you take two of these and have 2-pack voltages and turn the state out?
Yeah, great question. This is something that we're working with Curtis a little bit on right now. Main thing I want to do is prove that we can do it. And now we're going to go to Curtis and start putting a lot more pressure on them to build us something a little more specific for this application. Right now we've got 4 of these acuity devices. They're about $225 a piece. So that's kind of, you know, expensive by the time you buy 4 of them, like $1,000, you know. So we're going to start putting a little bit of pressure on Curtis to create one that has, you know, at least 2 inputs to tap 2 banks, if not 4. Now, the other nice thing about the acuity device is it also has a temperature sensor on it. So we can do the low temperature control of the charger. So when we're below that 32 degrees Fahrenheit, we can, you know, back off the charge current and trickle charge the batteries until they warm up. You know, because all of that information, battery current, our amp hours consumed, our amp hours returned via the charger, battery temperature, and even history of the batteries is all available on the canvas from the acuity unit. So it stores a lot of information and it can give us a lot of information. We only have to use one of the devices has to have the current sensor. The rest of them do not. So that's one of the things we're going to go to Curtis with, and this is one of the reasons why Steve Wade is here, is because we're going to take him out back and beat him up later. And get him to build us something that's going to be a little bit more specific for this application so we can get the cost down.
Yeah, it seems like if you could just do 2 voltages and 1 current, and you have the software to run the Alpine charger in there and the display for your little meter,
Right.
You've got a package.
Yeah, we've got a package. And this is, you know, after, you know, I came to EVCON last year and I thought, man, I'm going to get in front of these people and I'm going to convince them that a BMS is the way to go. Yeah, it didn't work out so well. After conversations with Nick Smith, with Jack, John Hardy, and a few other guys, I started sipping the Kool-Aid. Before you know it, I go home and I'm taking BMSs out of my cars. And I didn't take them completely out. What I did is I still strongly feel that we have to monitor the batteries. At least, we don't need to manage them. We've proven, Jack's proven, a lot of us have seen it. They don't need management. They just need to be checked up on occasionally. And if you get a cell that goes sideways, it would be nice to know that that happened. And so we went back last year, and I was scratching my head. I'm just like, man, damn those guys, they got me. I got to rethink this whole BMS thing, you know. We wrote controller software to be compatible with the Orion BMS and the Lithium BMS, and we got all this stuff talking and doing its stuff, and then I come out, and the first thing I did when I got home is I adjusted the parameters so the active balancing no longer works. But I couldn't remove it because you still have to control the charger and keep an eye on things. And
We've never been opposed to monitoring, but we don't want to burn our car and house down doing it. And we don't want to unbalance an already balanced pack for
Right.
parasitic loads.
And that's something that I wasn't understanding. It took me a little while, and it was probably on the plane ride home that I got my head wrapped around. It's like, oh my God, we're bleeding power off of the weakest cell. Why would you do that? You know, and only for the strongest cells to catch up to it, and still you can't use the energy that you put in them. So, you know, so the first thing I did is I got back, you know, the whole thing with the Corvette, found 12 bad cells, not because of BMS, because they were old junk cells laying in the corner, but the first thing we did is we paralleled them all up, and I connected my big old resistor on there, and we bottom balanced. And We took them down to the 2.5 volts. We let them sit for a couple of days, charged them back up. It's like, wow, look at this. They're all the same voltage. And
How could it be?
yeah, how did that happen? How is it that Jack can be right? So then we did the Corvette, and it's like, okay, let's do the Scion next. And so we went through the Scion, did the same thing they did. You know, my guys spent 2 or 3 days taking all those bus bars off, put all those jumper wires in, and deactivate the active balancing, and then the force was the next one after that. And I'm like, wow, it actually works. And I just wasn't, I was having trouble because, here again, I drank the BMS Kool-Aid for a little while. And it just, after talking to you guys, it's like, oh, man, you got a point. And so now how do we monitor it without having to buy this BMS that's going to be, $1,600, $1,700 for, what do you say, $50 worth of components. And so we've got the security device, so there's got to be something we can do. And so that's when we just kind of decided, with the upcoming stainless steel motor, and then I have to go into my boss's office, which is my wife, and say, okay, I need a check for a boat. And I go, what? You just built the Corvette last year. What do you need a boat for? You already got a boat. And so it's been a learning experience. But this seems to be a good. I know that Ed Boss has got another, and I'm not saying that this is the way to do it. I know that there's probably a lot of us out here that are working on something because there is a need, and this may not be the holy grail.
You do understand that living BMS free one day at a time started with a search for a BMS.
Because, well, the thing is you couldn't find one, and my BMS ventures started in 2008 when we built our jet, and we got a set of Thunder Sky 90 amp hour cells, and we needed a BMS, so we had to buy the cells. Oh yeah, we're working on a BMS. It charges the cells to 4.25 volts. And I was like, wow, that's cool. Until one of them shorted out and destroyed a cell. And then it's like, well, that didn't work, so now what? I've had really good luck with battery management systems. We worked our way up from that thing that Richard Hatfield built to flux power, which seemed like it was a really good idea at the time until it started killing cells just because its parasitic draw is so high. You connect it to a bank of cells, and in 3 weeks they're dead because the BMS is drawing that much power from it. So I was like, well, that's crazy. And then Orion and E-Lithion, and they seem to be getting better. But now it's this whole thing, it's like, why are we bleeding power off of the weakest cell? It just doesn't make sense. And thank you, Jack, for hitting me in the head a couple times and making me realize. Yes?
Brian, I had a question. Not ever being a boat owner, never been water skiing before or anything like that. The new electric motor takes up so little space compared to the gas engine, and if going at higher speeds draws that many more amps and that much more power, is there room to put a transmission in it? Do transmissions work on boats?
Completely unnecessary.
Okay.
The main thing about a boat is it doesn't take a lot of horsepower to get it moving, or torque to get it moving. It's just that your horsepower curve continually climbs as you go faster. So faster, more horsepower. Where a car, you got to have that torque to get the thing out of the hole initially, and then your torque drops off. So a boat, it's kind of backwards. They've tried transmissions in boats, mainly so that you can have a ski mode and a cruise mode. There was even a company that made a propeller that the propeller changed pitches as you were driving. And all that stuff has kind of gone away, and they do it all in the design of the propeller now, where it's got a certain amount of slip to it at low speeds or under high torque loads until the thing gets up and goes. But with electric motor, having all that low end torque anyways, it really doesn't matter.
The drag is a square function, but it feels like a cubic one in a boat.
I think it is cubic. I think it actually is.
My initial thoughts, what I know about pumps and pumping water.
Oh, is it?
I think it actually is, yeah.
I was thinking double the speed would be 4 to 5 times the horsepower. It didn't work out that way because when you get up on a plane, the hull becomes really efficient, and 2,200 watts per mile, it just kind of levels off there. So I'm sure different hull designs will give better results. We'll see what yours does. I think the jet is going to gobble power, but we'll see. Hey, this is how we come up with this stuff. Your mistake maybe save somebody else. And we're like, on these boats, being really nice, lightweight. Gets up onto a plane really quick, he's probably going to have better results than we did with this big slug.
Yeah, I don't want to drag this on much further, but regarding the oil cooling, do you cross drill through the armature or the rotor
No.
to get? And if you did do that, if you put a kind of a radial twist to it, it might act as like a pump.
If you cross drill the rotor, you're going to lose your rotor back. Just screwed yourself in efficiency. Yeah. So,
Okay.
Yeah, the rotor that we used to use cross drill rotors, and this new rotor design is solid because we're running a lot bigger bar than we used to in the rotor, and we need that back.
So, not being a software engineer, it might be an obvious answer to this question, but I have handled many ice automotive engines, and I've never seen a key shaft on the power uptake of an automotive engine. And I'm wondering, when you're designing an electric motor for an automotive applications, what do you think the advantages of a keyed shaft might be?
Universal fit. One size fits all. You have a hub made or a coupler made, and you slide it on that universal shaft. With the numbers of, we've sold in the on-road world, I'm not sure how many, let's say 500 motors. I'll bet you there's probably 250 different types of cars that they've gone into. And if you limit yourself to one flange or something like that, then you've just kind of screwed yourself because it'll only fit that in one type of car. To make multiples is going to get really expensive. So with the keyed shaft, and this is the way Warp does it, and Advanced DC is you buy the coupler that goes to your car, you slide that onto the keyed shaft, and you go, and keep the cost down. Now, if we've done OEM projects like the WeGo and the Miles vehicles and the Vantage vehicles, where we did create a flange, a shaft, a coupler for that application. But you're talking a company that buys 30 or 40 of them a month. So when you're doing that kind of volume, then you can afford to do something a little more specialized.
I'd like to add to that the keyed shaft is kind of an inherited thing. I don't know very many applications where they've relied on the key. We use a quick change, what's called a quick change coupler, but it actually compresses the shaft. We're not relying on the key to turn the car. And that's, we line it up with the key. but there's usually some other mechanism lock.
Yeah, a taper lock is a
taper lock or quick change.
And that's, I've seen a couple different iterations of these hubs, and there's some of them that slip on, use the key, and set screw. Not really good. I'm kind of partial to either the taper lock or the ones that are, the hubs that we've built, we usually make them out of aluminum. There's no need to make it out of steel. And we make them to where the bore of the aluminum hub is 3/1000 under the shaft size. We warm it up and slide it on. And once it bites down on that shaft, it's not going anywhere. So
You had mentioned something about the power shifting props. Did you ever try any, or you just thought about them?
Can't even buy them anymore.
You can't, okay. I
Yeah.
personally have one
Oh, you do?
somewhere.
Okay.
I've got a 26-foot Celebrity cuddy cabin.
Okay.
And I've been on boats since I was in my mother's womb. But what it will do is, yes, you've got plenty of torque on your low end. But when you're propping down from 17 to 15, and even if you're double cupping your edge of your prop, which then helps you get your out of the hole shot. But then when it hits a couple thousand RPM, about 3,000, 2,800 RPM, it'll shift.
Right.
And now you're spinning a 19 prop.
Right.
So now your top end of your boat will jump from 42 to 52
Right.
miles per hour. So there's some out there. I don't know if there would be any
Yeah,
goodness
I've
to that.
searched eBay because I was actually looking for, I think it was Land and Sea. that-
Land and Sea is what I
Yeah.
have, yes.
And I think Land and Sea is still in business, but they only build like dynos and that sort of thing.
Right.
I think now, but again, they're no longer making that torque shift. I think it was.
It might get you some better top end, because once it shifts, now it's the same as you're running a
Yeah,
19.
kind of in the boat world, you know, we're not looking at building 60 mile an hour, at least not yet.
Okay.
60 mile an hour electric boats.
Okay.
So, you know, and the performance was so good.
Yeah, 42 is good.
The outdrive is a 1.8 to 1 or 1.81 to 1 outdrive with a 4-blade 15-inch prop. And, you know, I mean, we probably could have gone a little faster if I, you know, really trimmed it out good, but it's like, wow, 42 miles an hour in an electric boat, that's pretty fast.
And these are only 3 bladed, so you might get less drag.
Yeah, yeah.
Other questions? What do you have back here? Anybody?
I guess that's a wrap.
Not very curious about boats.
I guess not.